Section 1.1 talks about introduction to systems of linear equations. So we want to set up a few terms and kind of follow up on certain forms of equations of lines or systems of equations of lines. So a linear equation in n variables, that is x1, x2, x3, all the way to kind of like x, y, z. You're used to kind of those. Well, in linear algebra, since we use a lot of these variables, it becomes a hassle to call them x, y, z, or a, b, c, d, e. We just call them x sub 1, x sub 2, representing kind of like x and y plane will be x sub 1, x sub 2. So this can be expressed as linear equation ax sub 1, ax sub 2, ax sub 3, ax sub n equal b, where a's a sub 1, a sub 2, a sub 3, those are called the constants, and they can't all be 0. Some of them could be 0, but not all of them, right? And the x's have a power of 1. That's where the linear relation comes from. And if b happen to be 0, then we call this system a homogeneous, or this equation a homogeneous equation. So again, think of it this way, like 3x plus 2y equal a 7. Now we're going to say 3x sub 1 plus 2x sub 2 equal a 7. And that's really how we're going to play with this. So first problem's pretty much asking you to figure out if these are linear or not. Here we are dealing with x and y. Well, you look at the variables. This has a power of 1. This has a power of 1. So this is linear. Yep. B, a power of 1/3. That's not a 1. So this is not linear. 3, cosine of pi over 7 is a constant. You only worry about the variables. The variables have a power of 1. So this is, and again, this is not a variable. This is a constant. Here, cosine of x is not linear. Now, what do you know about linear? Well, out of all the infinite types of equations that we come across, the only equation that's represented by a graph of a straight line is a linear equation. So if I was to graph those, this would be a line, this would be a line, this would be a curve, not a line, and this would be also a curve. Here, since you're multiplying x, y, so again, linear equation is a relation in which the variables are multiplied by constants. No two variables are multiplied together or divided. So this is not linear. The graph of this looks like one of those. And here the power on x is a 1 and y is a 1. So this is linear. The graph of that is a line. Well, that's for starters. So where are we going to focus? The title of the class is Linear Algebra. We deal with linear equations 99% of the time. Now, when we talk with linear equations, and we're going to talk about the most basic, which is 2 dimensions, systems of equations, 2 or more, consist of more than one equation. It could be 2 by 2, 3 by 3, 4 by 4. So if I'm looking at these systems, and we talk about 2 by 2, and we generalize for 3 by 3, 4 by 4, 5 by 5, but in general, one of two things happen if you are thinking about sketching 2 linear equations, and it has to be linear. And the reason for that is straight lines have very unique properties. One of 3 things could happen. I could get one solution. We call the system consistent. I could have no solution. We call the system inconsistent. And we could have 2 identical lines that would also be consistent. So if there is a solution, we call it consistent, but here we have infinite solutions. Okay, I'm having a hard time writing today. Infinite amount of solutions. Now, If we have more than one line, we're talking about two specifically. A solution to a system of equations would be the value of the variables that equate each equation in the system. So it's not enough for you to say I have a solution of this system and it happened to equate the first equation. If there are two equations, it must equate the first equation and the second equation. If you have three, first, second, and third, and so on and so forth. Now, one way to represent a system of equations is by what's famously known as an augmented matrix. Sort of like using syntactic division instead of long division. So, augmented matrix is when you take a system of equations and you pretty much eliminate the variables. So you want to make sure that all of these variables stand for x sub 1 and you just copy the coefficients. All of these variables are the same, so again you just copy the coefficients. Now they used to put a line right there to indicate the difference between the variables and the numbers, but lately they've been ignoring that. So a couple of books back, they've been really going back and not writing that, which makes things a bit confusing, but we can manage. So they would write it. Again, all of these are x sub 1, so you want to make sure that when you write a column, you're representing the same variable. Those are all x2. There's 0. Again, kind of like syntactic division. Whenever a variable is missing, you need to fill a 0 for it. And x sub 3 would be a 2, 4, and negative 1. Now, it used to be a line, but nowadays they're taking that line out. And that's how the augmented matrix look like. And if I wanted to write this as an augmented matrix, 1, and you notice there's nothing beneath it. Here, there's a 0, 1, 0, and 0, 0, 1. This is a very special matrix. And again, they're taking that out. But you could imagine there is the equal right there. Now, this is called reduced raw echelon form. It's really useful because you could tell that x sub 1 equal 1, x sub 2 equal 2, x sub 3 equal 3. The goal is to take each of those and make it look just like that. Now, to make it look like that, that's a lot of work. We do that in very special cases. In general, we just work out to make it a triangular matrix. We'll talk about what that means in a few minutes. This is an augmented matrix. They tell you that. Can you write the system? So again, there's the equal. This is 0, x1. So this is 3x1 minus x2 minus x3 equal a negative 1, and 5x1. And it's very important for you to line those up. Okay, you know what? I messed up big time. That's x1, that's x2, and that's what we're going to do all throughout. So that's 2, that's 3, and that's 4. So this is 5x1 plus 2x2 minus 3x4 equal a negative 6. So you want to make sure you line them up, especially when you want to write them as a matrix. This is the system of equations. Here we have, again, x1, and you could do that all the time. So we have 3x1 plus x3 minus 4x4 equal a 3, negative 4x1 plus 4x3 plus x4 equal a negative 3. And the third equation, that's this one, negative x1 plus 3x2 minus 2x sub 4 equal a negative 9. And as for the last equation, I only have negative x4 equal a negative 2. So normally that's kind of what we go for. And again, no need to really worry about anything I'm saying and not writing, because we're going to start working on those pretty soon. All right, well, let's talk about a solution. Here's a system of equations, and we would like to know, in each part, determine whether the 3 tuples is a solution of the linear equation. Well, for it to be a solution of a linear equation, it must satisfy the first equation. I replace x, y, and z by these values. I should get a 3. Replace those by those 3, I should get a 1. And in the third equation, I should get a 5. So we start with the first. If I replace x by 5 7 plus 2 times 8 7th, that's 15 7th, minus 2, we want to see if that equals a 3. Now, isn't this 21 over 7, which is 3? 3 minus 2 does not equal to 3. So this one is not a solution. If it doesn't satisfy any one of these equations, automatically it would not be a solution. If I attempt the second piece, take 5 over 7 plus 8 times 2, 16 over 7, minus 2 times 0, and let's see what do we get. Well, we'll get 21 over 7, which is 3. It checks. That's not enough. I still have to go on and attempt in the second. 3 times 5 over 7 is 15 over 7, minus 8 over 7. I want to see what that equals. Well, that's 7 over 7, which is 1. It checks. And if I go for the third piece, negative 5 over 7. 5 times 8 over 7 is 40 over 7. And negative 5 times 0 is 0. And what that equals, 35 over 7, which is 5. And it checks. So yes, that would be a solution. Now, the reason I'm checking this, even though those are linear equations, remember the infinite amount of solutions case. I could have infinite amount of solutions for a system of equations. Let's see if this works. If I take 5 over 7 plus 2 times 10 over 7 is 20 over 7, minus 2 times 2 over 7 is 4 over 7, what would that be? 25 minus 4 is 21 over 7, that's 3, that checks. For the second equation, 3 times the first, that's 15 over 7, minus 10 over 7, plus 2 over 7, what that equals over 7. 17 minus 10, 7 over 7, which is 1, it does check. And for the third, negative x, negative 5 over 7, plus 5 times 10 over 7 is 50 over 7, minus 5 times 2 over 7, that's 10 over 7. What that is over 7, that is 50 minus 15, 35, and that turns out to be 5, and we say yes. So you could have an infinite amount of solutions. There's no way of figuring that out. How about here? Under what conditions on A and B will the linear system have no solution, infinite solutions, or one solution? Well, let's see. If I am to multiply this by negative 2, wouldn't that become a negative 4x plus 6y equals negative 2b? If I add those, I'll get 0 equal a minus 2b. Now, let's talk about, and this is really the study of systems where we're going to focus on. Basically, this part. When do you have no solution, one solution, infinite amount of solutions? This is saying 0 times a variable, whatever it is, x or y, equal a minus 2b. So a minus 2b is a number. And here we're going to take a variable, let's say 0 times x. Well, we're kind of limited. That is, 0 times x is always 0. So if a minus 2b doesn't equal to 0, then I'll get no solution. Which means what? If a doesn't equal to b, I'll get no solution. If a minus 2b does equal to 0, so if a equal 2b, if I am to replace this a by 2b, I'll get 0 equals 0. And anytime you get no variables, just numbers equal, this is the infinite amount of solutions. And as for the one solution, that's not possible. the fact that one of those zeroed out pretty much limits you to either no solution or infinite amount of solutions. And we'll elaborate on that again when we get to these problems. So now this is something we have to adjust to. This is something that does come up in college algebra, but a lot of times it's overlooked. And let me put it this way. Let me start with this. Then I'll go back to those. It says each certain equation has an infinite many solutions. Infinite many solutions. Use parametric equations to describe the set. Let's say it just says solve. If a problem says solve, what you do, you say, okay, well, let's see. I'm going to multiply this bottom equation by a -2. So the system becomes the top equation 6x sub 1 plus 2x sub 2 equal -8. And -6x sub 1 minus 2x sub 2 equal 8. When you add those, you get 0 equals 0. Anytime this happens, anytime the variable cancel out, it's either you have an infinite amount of solutions or no solution. If the variables cancel out, you're left with numbers. If the numbers are equal and you get a true statement, that means infinite amount of solutions. And if the numbers are not equal, you have no solution. But you can't say all real numbers. For example, 0, 0 doesn't work. 6 times 0 plus 2 times 0 doesn't equal -8. For it to work, I need a correlation between those. And the way it works, let's say I picked x sub 1 to be t. You could use any letter. If I let this be t, wouldn't x sub 2 equal -4 minus 3t? And of course, you are welcome if you want to call x sub 2t. And if you call x sub 2t, then 3x sub 1 plus t equal -4. Move that over and divide by 3. So that will be -4 minus t divided by 3. So here, what's t? T could be any number. Either way. So here, if I pick 0, for example, 0, -4 satisfy this equation and this equation. If I pick t equal 1, 1, -7 satisfy both of those. Over here, t equals 0, -4/3, 0 satisfy both of those. So either one of those will do. That's called a parametric equation set. And here, if I take the first equation, so call this equation 1. If I multiply 1 by 2, 2 times equation 1, and add it to this, that would be 4x1 minus 2y plus 4z equal a -8. If I add it to this, I'll get 0 equals 0. And if I take -3 times row 1, I'll get -6x plus 3y minus 6z equal a 12. And if I add that to equation 2, now you notice how messy this is to say. Well, we need to establish a way of doing that. So we start calling this row 1, this is row 2, and this is row 3. And when we want to do something like this, we say take 2 times row 1 and add it to row 2 and row 3. And when we want to do this this operation, we say take -3 row 1, add it to row 2. And that's really how we're going to start doing things. But if you notice those zeroed out, well, here now we have 2 things to worry about. Now look for the easiest way out. If I call this z t, and I call y any other variable, say c, wouldn't 2x minus c plus 2t equal -4? Move those over and divide by 2, and that's how these are related. -4 plus c minus 2d divided by 4. That would be the solution, where t and c could be any numbers and they don't have to be the same. Now if I go back to what they want us to do, they're saying parametrics describe the linear set, right? Say this is an equation. If I let y equal t, and it's your choice, wouldn't that mean x equal 2 minus 10t? And what's t? T could be any number. Kind of like me saying, give me two numbers that add up to 10. Well, if you let y equal t, then x should be 10 minus t. And these are the two two values that will add up to 10 every single time. If x equal 1, 9, 9 and 1 will add up to 10, and so on and so forth. So that's really what you're doing. And if I have 3 of those, well, pick the easiest one. Normally, you could pick them any way you want. Pick the one that doesn't require division. So let this be t, let this be c, and wouldn't that mean that x is 3 minus 3c plus 12t? And that would be the parametric equation for the system. And here I have 4 variables, but notice this doesn't require any division. So if I let the first one be t, now that's 4t. The second one be c, that's 2c. And tc and k supposedly, again, any letter will do. What would x4 equal in terms of those? Oh, that's 20, not 40. Wouldn't that be 20 minus 40 minus 2c minus 3k? And that's considered a parametric equation where t, c, and k could be any number. Here, c and t could be any number you want. And again, they don't have to be the same number. And if I look at this again, it says find a single elementary row operation that will create a 1 in the upper left corner. They want this to be a 1. One way of doing that, again, remember, we're going to call this row 1, we're going to call this row 2, and we're going to call this row 3. And if you're overwhelmed with everything I'm telling you, we're going to do that all throughout the course. To make this a 1, if I take 3 times row 1, wouldn't that make that a 6? And add it to row 3. Put the result in row 1. That's how we're going to do operations. So if I multiply row 1 by 3, isn't that a 6, a 12, negative 18, and a 24? And if I add it to the third row, negative 5, 4, 2, and 7, wouldn't that be 1, 16, negative 16, and that will be a 20, that 31? There you go. That's a 1. The rest, it doesn't matter. That's all they want us to do. And if I wanted to apply that on B, well, if I took row 1 and added to row 2, but put the result in row 1, what would happen? So if I add this and this, well, negative 6 plus 7 is a 1. 3 minus 4 is a negative 1. Negative 1 minus 2 is negative 3. And 4 plus 2 is a 6. And that's all they want. And lastly, this is crucial, find the value of k for which the augmented matrix is consistent. It has a solution. We start by really eliminating those variables. That is, this is row 1 again. So wouldn't you say multiply this by 2 and add it to that? Take row 1, multiply it by 2, add it to row 2, and put the result in row 2. What would happen? Well, let's see what would happen. 3, negative 4, and a k. If I multiply row 1 by a 2, wouldn't that become 6, negative 8, 2k? And if I add it to negative 6, 8, and 5, wouldn't that be 0 plus 0 equal 2k plus 5? So 0, 0, 2k plus 5. Notice, this says 0 times a variable. Let's say 0 times x2 equal 2k plus 5. But here I'm limited. 0 times any quantity is 0. The only way I can get a solution, since the variables canceled out, if those are equal. So if I want a system to be consistent, I must insist on 2k plus 5 equaling 0 or k equaling negative 5 halves. If k equal negative 5 halves, this will be a consistent system. You'll have an infinite amount of solutions, but that's consistent. And if k doesn't equal 0, then you'll have no solution. Similarly, if I take this and I start by saying, well, let's see, if I add them, those cancel out. If I just take row 1 plus row 2, this is row 1 again, and this is row 2. Wouldn't I get, and again, there's the equal, right? This is on augmented matrix. So if I add those, I'll get 4 plus k, that's a 0, equal a 0. So here, I'm looking at 4 plus k times some, say, x1 or x2, it doesn't matter, right? If 4 plus k equals 0, I'll get 0 equals 0, that's a solution. If k equals negative 4, I'll get a solution. And if 4 plus k doesn't equal 0, if it equals 3, if 3x1 equals 0, doesn't that mean x1 equals 0? So if k doesn't equal negative 4, I'll also get a solution. What does that mean? That means if k is any number, I'll get a solution guaranteed. So there's a big difference between me saying 0 times x equal 0 or 0 times x equal 3. That has no solution because this is 0 equal 3. There's no way of fixing that. Versus x times a number equals 0. Well, this has a solution because if I divide by 3, I'll get x to be 0. And the homework will be as listed right there. And that's pretty much it for this section.